Alright everybody, welcome back. In this video we are going to talk about material from section 10.5 of AP Calculus, BC, harmonic series and P-series. So we're going to talk about what P-series are, when they converge, and we're also going to introduce you to, and I've hinted at in previous videos and lessons, the most famous of all the infinite series, the harmonic series, which is a particular type of P-series. So let's start with a definition of what a P-series is. A P-series is an infinite series of the form sum from 1 to n, or pardon me, sum from 1 to infinity of 1 over n to the p power. So p is the power here in our P-series. We've got our basic, variable of our summation raised to the p power. So for instance, this series 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, etc., etc. Wherever p is greater than 0, because if p is less than 0 here, this is really a summation of this form, which we should know that all of these are going to diverge because they don't approach 0. Or at least when, anyway. It's neither here nor there. So these are our P-series, and these all behave in a specific fashion, and those are the series that we're going to talk about today. All right, example 1. Identify which of the following are P-series. At first, this one does not necessarily look like one, but with some simple algebraic manipulation that you've done millions of times before, this series can be written as sum from 1 to infinity of 1 over n to the third power. Okay, so it's written in this form, sum of 1 over n to the p. P is greater than 0, so yes, this is a P-series. Okay, the next one. We've got 1 over 3 to the n power. Now, in this case, when we're talking about P-series, p is our power. That's a constant value. In this case, we've got a varying exponent there. This is actually an exponential geometric series, since we've got the exponential in the denominator. No, this is geometric, because for a P-series, the base of the exponential should be n, and the exponent should be the constant. And then this third one is very similar to what I just talked about in the very beginning. I can rewrite this as sum from n equals 1 to infinity of n to the 1.2. But to begin with, in this form, this is not a P-series because p is less than 0. Okay, so that's how we can recognize series that are P-series and series that are not P-series. The next thing we talk about here in the box, the harmonic series, the most famous P-series and probably the most famous of all the infinite series that we talk about. The sum from 1 to infinity of 1 over n, and that's of course what the terms look like. It's strange to talk about a series as famous, but as far as infinite series go, this is the most famous, and I like to think that it is the most famous because it is the dividing line between the convergent and the divergent P-series. Every P-series where P is bigger than the p-value in the harmonic series converges, and every P-series where P is smaller than the P-series in the harmonic series diverges. And we see that in this next box below, the convergence of a P-series. It's going to be very straightforward for us when we are trying to find the convergence of a P-series. We see the sum from 1 to infinity of 1 over n to the p. If p is greater than 1, it converges. If p is between 0 and 1, it diverges. And so that's how we're going to identify when P-series are converging P-series or diverging P-series. Let's go ahead and we'll go to the next page, and we'll look at example 2, where we're going to decide for all of these series whether they converge or diverge. Not all of these in this set are P-series. Most of them are, but not all of them are. All right, let's look at the first one. Sum from 1 to infinity of 1 over n squared. Okay, this converges because it's a P-series with p equal to 2, and 2 is greater than 1. Okay, a lot of times if I'm, explaining this, I'll just write this like this, with p equals 2, which is greater than 1. All right, this p-series, is it a p-series? Yes, it is a p-series. The sum from 1 to infinity of 1 over the 4th root of n could be rewritten as the sum from 1 to infinity of 1 over n to the 1/4 power. This one diverges because it's a p-series with p equals 1/4, and 1/4 is in between 0 and 1, so it diverges. Okay, next one. Again, when we have roots and stuff like this, we want to convert those over so that we can see whether it's a convergent. And we don't necessarily have to rewrite them, but at least in our head, we want to be converting these over to rational exponent form. This one converges because it's a p-series with p equal to 3/2, which is greater than 1. All right, part D. This is not a p-series. This is a geometric series. And the r value in this geometric series is 4/3. Geometric series with r equals 4/3. Absolute value of 4/3 is greater than 1, so it diverges. This one is a p-series. Okay, this diverges because it's a p-series with p equals 3/4, and 0 is less than 3/4 is less than or equal to 1. All right, so we found the first 5 here, whether they converge or diverge. And now we're to example F. It's not a p-series, it's not a geometric series, but this is one of those series that we could use the integral test to determine. This is, in fact, I'm pretty sure we have done this one. This is positive. It's continuous. Oh no, we haven't, you know what? And ooh, this is not decreasing. I'm sorry, we don't need the integral test. I was about to make this way too difficult. We don't need the integral test on this. Let's just take the limit as n goes to infinity of a sub n. And so this is the limit as n goes to infinity of n natural log of n. That limit is equal to infinity. Therefore, this one diverges by the nth term test. Since in order for it to not be divergent from the nth term test, this limit has to be equal to 0. All right, there we go. We found whether all of these converged or diverged. Little refresher on geometric series, a little bit thinking about the integral test, the nth term test. So, we're building this, again, I keep saying this, we're building this toolbox, and every lesson we have, we add one more tool to the toolbox with which we can find whether or not a series is convergent or divergent. Let's go ahead and look at example 3. For what values of k will these series converge? This is a p-series, clearly a p-series, and p is equal to 3k plus 2. In order for a p-series to converge, the p-value must be greater than 1. So in order for this to converge, 3k plus 2 has to be greater than 1. And solving for k, we get that k has to be greater than -1/3 in order for this to converge. The next one. This looks a lot like a p-series, but we have to rewrite it first. This is the sum from 1 to infinity of 1 over n to the 2k minus 5, which is what we get when we multiply these two expressions containing n together. And so in order for this to converge, we need 2k minus 5 to be greater than 1. We add 5 to both sides, divide both sides. So in order for this to converge, we need k to be greater than 3. And in this last one, we have an n in the numerator, which complicates things a little bit for us. What we're going to do is we're going to factor an n out of both the numerator and the denominator. In this case, we're going to factor an n out of both numerator and denominator, which turns this part into 1 over, and when we divide this by n, it becomes n to the 3k, and this becomes 3 over n. Okay, now n over n is equal to 1, so we can get rid of it. So really, this is equal to the sum from 1 to infinity of 1 over n to the 3k plus 3 over n. Now, this is not quite a p-series, but what we will find out here is that this piece right here, as n goes to infinity, this piece right here goes to 0. So as n goes to infinity, this becomes something that is closer and closer to a p-series. And because of that, we're going to use our same convergence idea here for p-series. We need the p-value in this expression to be greater than 1. And that tells us that we need k to be greater than 1/3 in this example. All right. And we will talk more about other ways that we could show the convergence or divergence of something like this later on. I feel like I keep saying that. Later on, we're going to learn more that's going to enable us to do this. And that's so true when we're talking about infinite series. We're building the toolbox. Another tool in the toolbox now. We now know how to determine whether p-series converge or diverge. And so at this point, we've got partial sums that we can use for convergence and divergence. We've got geometric series ideas that we can use for convergence or divergence. We can use the nth term test to decide if something diverges. We can use the integral test to see if something converges or diverges. And now we can use what I've always just referred to as the p-series test. It's not really a formal test, but just the fact that when we have a p-series, the value of p is greater than 1 gives us a convergent series, and less than 1 or equal to 1 gives us a divergent series. All right. That brings us to the end of section 10.5. Join us next time for section 10.6, which I'm forgetting what section 10.6 is off the top of my head right now. So it'll be a surprise when you join me next time. All right, have a great rest of your day, and I'll see you when I'm seeing you. Bye-bye now.